d'abord présenter le jury. Donc, nous avons deux rapporteurs. Donc, ils sont tous les deux à ma droite, Joël Bélessa de l'ILM à Lyon et Nathalie Katsonis de l'Université de Twente aux Pays-Bas. Nous avons ensuite deux examinateurs, Sylvain Barbet du C2N, Steven de Feiter de l'EN et puis donc votre directeur de thèse, Fabrice Chara du CEN. Très bien. Moi, je suis de l'Institut d'optique Jean-Jacques Greffe. Eh bien, vous avez environ 45 minutes pour nous présenter vos travaux, et puis ensuite, il y aura une séance de questions.
Ok, d'accord. Merci, Monsieur le Président. Donc, aujourd'hui, je vous présente mes travaux de thèse qui ont été effectués au CEA sous la supervision de Fabrice Chara. Et je vais passer à l'anglais pour la présentation de ce travail. So, in this work, we study if and how we can use supramolecular self-assemblies coupled to plasmonic devices towards the realization of more efficient photonic nano devices. Okay. So, as you know, miniaturization is a main objective for in a lot of fields. Why miniaturization? Because it can increase the functionality you can put on the same footprint for your devices. Because you have a smaller device, you also need less energy in order to your device to work. You reduce also the amount of material you need to build your system. And then because it's smaller, you can make your device work at a higher frequency. So the electronic community has done this quite well, reducing sizes to almost 10 nanometers for devices. But for the photonics community, it has been quite harder, for example, to shrink the size of laser, because at one point you have a physical problem, which is the diffraction barrier. So if you consider, for example, here a typical laser cavity, where you have two mirrors and the light bouncing between the two mirrors, you have this standing wave. And to have this standing wave, you have a relationship between the distances, between the wavelengths of the light and the length of your cavity. And if you want to shrink this device, at one point you are in this configuration and it's not possible to shrink anymore the device. So what happens if you do this to shrink more the size? In fact, you will have, doing this, you will have losses, because now, since you don't have two nodes at the end of the mirror, at the location of the mirrors, you will have destructive interferences between coming light and reflected light, so you will have losses. And because you are in where the regime where the mirror are very close, you will have we will have to deal with evanescent waves. And all this physics going on at the interface between the surface of metal and dielectrics is called plasmonics. So there are two kinds of plasmons, either propagative surface plasmon at an interface between, for example, air and metal. And there are local surface plasmons located on, for example, on a nanoparticle, the gold or metallic nanoparticle. And the characteristics of these waves, in fact, the nature of these waves are not only electromagnetic, but it's a coupling between the electromagnetic field and electrons in the metal. But these waves, they have the characteristic of being very confined at the surface of the metal here, or in the vicinity of the nanoparticle. So what are the applications of this plasmonics system? If you deal with nanoparticles, you can have some passive application, passive device application for photo detection, for emitting light, for in optical tweezer or for heating. And if you use these propagative plasmon polaritons, you can have some application of sensing, waveguiding the waves, and also metamaterials, modifying the electromagnetic field. So in our case, because all of these are passive devices, we ask ourselves, would it be possible to deal with active devices? And the motivation is to realize, to miniaturize active devices such as lasers, switches, frequency converters, using these plasmonic waves. So how to build active devices? To build active devices, you really need nonlinearities. And this nonlinearity, you can find it with stimulated emission of plasmons. So if you look at the rate of stimulated emission of an emitter sitting on the top of a plasmonic waveguide, you have this kind of expression. And you see that there are 4 factors. The first factor depends on the characteristics of the metal that you use and the dielectric that you have on top of the metal. And you see that for a gold plasmonic waveguide, it's better to work in the red region of the spectrum, which is above 600 nanometers. The second factor is related to the oscillator strength of your emitter, meaning that your emitter have to interact a lot with light to optimize this rate of stimulated emission. The third factor is a spatial overlap. Of course, if you put your emitter far away from the mode, you won't be able to transfer the energy. And the last factor is as well the spectral overlap. If you have a blue emitter and you want to amplify a red mode, you won't be able to transfer energy as well. So, okay, we have a bit of insight about how we should optimize this stimulated emission. How to build this kind of active layer on top of plasmonic system. In fact, you have 2 strategies. You can use a top-down approach where you build devices from the top, such as with lithography techniques, which is commonly used in the semiconductor industry. But you have also a bottom-up approach, which is called, for example, molecular self-assemblies, meaning that you start from building blocks, and the assembly of the blocks create this new material that you want. And here, the drawback of this technique is that to build a special geometry, you have to include all the information of this geometry in the building block. So you won't be able to build as complex a shape as you can do with the lithography technique. But in turns, it's very easy to use this technique. It's much more efficient, and you're still capable of building quite complex shape, for example, with DNA. So, in this work, we will use this self-assembly because you could exploit some very strange physical phenomenon going on here, because the molecules are very close from each other. And because they are very close, you can expect some collective effects between the molecules. So what are these collective effects? In fact, if you have molecules close from each other, you can expect 2 kinds of couplings, a side-by-side coupling and a head-to-tail coupling. Side-by-side coupling is in the case where your dipoles are sitting side by side. And in this case, you will have this new system where here the lower level is non-radiative. So all the transition will be to the higher level. And therefore, in comparison to the characteristic for the isolated molecule, you will shift the excitation frequency to the blue. And in the head-to-tail coupling, in this case, it works at the opposite, and you will have this level which will be radiative and this not radiative. So you will shift to the red the excitation frequency. And what is important here to note is that here the fields are coherent, meaning that if you consider the overall system, you will add the two fields, and therefore you will have a quantum emitter that have a higher oscillator strength, which is good for the stimulated emission of plasmons. Okay, so taking advantage of these effects, we ask ourselves, would it be possible to use these self-assemblies for the amplification of plasmons? So the advantage of this system is that you have very high density of emitter at the surface of the gold, the plasmon waveguide. And what you have also is these intermolecular couplings that I talked to you about. But as a drawback, here, most of the systems that we know are 2D. And because they are two-dimensional, they do not have a good overlap with the plasmon mode, which is in 3 dimensions. So your spatial overlap will be quite low with this system. And another drawback is the fact that the energy could go as well to the substrate and not radiate to your plasmon mode. And this will affect a lot the capacity of giving the energy from the emitters to the plasmon mode. To have a bit an insight about this, all these characteristics, we did little calculations to compare ideally what we could obtain for gain comparing conventional gain media and or self-assembled system. So we'll compute the gain for dye monolayer, self-assembled dye monolayer on top of a substrate, and kind of ideal system where you self-assemble pillars of coupled molecules. So if you compute the oscillator strengths, so here it's absorption cross-section. Basically, well, for the PTCDI, it's quite the same as the traditional gain media. But you have a very high volume density, so it's quite good. The thing is, you have a very poor spatial overlap, so at the end, you won't be able to surpass the capabilities of this conventional gain media. But if you have these dye pillars, because you have the intermolecular couplings, you will exceed a lot the absorption cross-section and fluorescence cross-section, keeping a same volume density because the molecules are so close from each other. And you have a quite good spatial overlap because now you have a 3D system. And at the end, with this kind of system, you could eventually surpass the gain that you usually have with conventional gain media. So we have some problems miniaturizing photonics, and we can get around using plasmonic waves. These plasmons, they put new constraints on the optical gain media you have to use to amplify these modes. The question is, for this work, can we use dye self-assemblies to amplify these plasmons and be kind of the next generation of optical gain media for nanoscience, nanotechnology application? After this introduction, I will first begin by studying these supramolecular self-assemblies, since their optical and photonics properties are not well known. And This first step will give us some insight about using these systems. And then we will go to three-dimensional self-assemblies and see if they are suited for amplifying plasmons. The first system that we studied here, the model that you can see, is a 2D supramolecular self-assembly on graphene. Why graphene? Because graphene is structured as at the nanoscale, so it's a template for the building of the system. Graphene is conductive, so you can perform some scanning tunneling microscopy and really see the structure of the network and being able to know at which distance the molecules are apart. But graphene, because it's so thin, it's also transparent, and this property will be very useful doing optics experiments because of this transparency. And last, this system is quite interesting because graphene is transferable on a lot of surface and devices. So you can really easily think about transferring graphene on a SPP plasmon waveguide and building your self-assembly on top of it, or to a nanoparticle and building also kind of nano laser with this geometry. So what can we characterize on these systems? First, we can use scanning tunneling microscopy to reveal the network of the supramolecular network. We can do some optical microscopy to see the surface and see if there are any defects at the micron scale. We can perform some absorption microscopy to see how the dyes and this hybrid system absorb light. We can do some photoluminescence microscopy as well to see which light is emitted from these devices and see what is the dynamic of this fluorescence emission with some film setup. And then we can also do some study on the vibration of this hybrid system with Raman microscopy. So in our first system that we study, we use this dye, which is a perilene derivative with here C13 alkene chain at the extremity of the aromatic core. And why is this molecule? Because this molecule is well known for optical scientists as a good dye and for the surface science community because people have done already some work on graphitic surface. And as you can see on graphitic surface, such as highly ordered pyrolytic graphite, you have a square network, which is the same on graphene on copper or graphene on top of a PET surface. And you see that you have a square network here of the molecule symbolized by the yellow color on the images. On the optical side point of view, this molecule has an optical dipole moment along the NN prime direction and display an absorption spectrum which is typical of pi-pi dye, pi-pi conjugated dyes with the principal resonance here and some vibronic replicas which are related to CC vibration in the aromatic core. So, as you can see on this image, the dyes seem to lay flat on the surface. And we wonder if it's possible to validate this with optical experiment as well. So, in fact, it's possible to see that because if you have dipoles parallel to the graphene surface, seeing how the absorption varies with the incident angle, when varying the incident angle, you will have two behavior if you are transverse magnetic or transverse electric polarized. And that's what we saw with the experiment. Here the experiment in square and triangles, and here the theory in plane lines. And you can see that this theory explains very well what is going on. So we are confident in saying that we keep the anisotropy of graphene with this monolayer of dyes. Okay, so now what is the absorption spectrum of this hybrid system? Here you see the absorption spectrum of the dye in solution, and here self-assembled on the graphene surface. The first thing that was very interesting for us was to see that you have almost macroscopical optical absorption. You can almost see with the eye the color of this hybrid system. And it's just one molecule thin, so it's quite impressive. And you see that this system absorbs 2% of the light if you have just one side, and 3.6% if you have two sides. The second thing was quite impressive for us. That was quite impressive for us was this redshift of the overall spectrum. You see that you have, sorry, I forgot something. So we were wondering here if this huge absorption was correlated to kind of enhancement effect on the surface. And in fact, to verify this, you can compute the molecular absorption cross-section by two ways. Because you know the surface density of the molecule with the STM experiment, you can find quite easily the absorption cross-section. And you find also the absorption cross-section from dyes in solution. And you see that the numbers are quite close. And therefore, we are confident in saying that there are no enhancement effect. It's just the fact that the dyes keep their oscillator strength from the solution to the surface. So, as I said, now we interest ourselves to this shift of the whole spectrum towards lower frequencies. And this shift is quite big, meaning that here we have the modification of the electronic structure of the dye. And this is confirmed as well by the broadening of the peaks. This can due to inhomogeneous broadening effect, but in this case, the supramolecular self-assembly there are not a lot of defects, so we are more thinking about modification of the dye electronic structure. If you want to use this system for engineering at the nanoscale, you really need to understand why there is this shift. And understanding this was the next question in our work. So which phenomenon are responsible for these changes? So there are two phenomena that can going on here. First, the molecules can interact between themselves, but you can also have interactions with the graphene surface. And in the first part, we will study the intermolecular interactions. So, as you know, if you have a media, the polarizability of the medium is different from the polarizability of the isolated emitter. And this is given by the Clausius-Mosetti relationship, where you see that the poles of this polarizability will be different from the poles of the isolated emitter emitter. And so you will have a shift of the spectrum from when you just look at an assembly of these emitters. So this is for the 3D case. And in fact, for the 2D case, you can have the same approach and develop a general formula for the polarizability of the overall system. And you see that you only have this K constant here, and this K is related just on the geometry of the assembly here. So if you are in a head-to-tail configuration, which is a G-like configuration, you will have this positive K constant, and side by side, H-like configuration, you will have a negative K factor. So if we do some simulation here about these two situations, you see the absorption spectrum in black. In this configuration, using the formula, will be shifted to the red, and in this configuration will be shifted to the blue. So if we use the STM, the network data that we extracted from the STM experiment, and we implement this in our model, we predict the same kind of redshift that we see experimentally. But this redshift is a bit bigger than what we observe, almost 300 millielectron volts in comparison to 100 millielectron volts, 140. Therefore, we think that graphene is acting, is shielding the electron. He's doing some screening effect of the electrons. And you see also that this classical model is not good at explaining the overall shift of the spectrum because the vibronic replicas are not shifted. So this is a bit of theory. What is going on in reality? We found that this molecule, which is the same aromatic core than the previous one, with a different here substitution at the extremity, also self-assembles on the graphene surface, but with a very different supramolecular network. And this way, you keep the di-graphene interaction, and you vary only the intermolecular interactions. This supramolecular self-assemblies, in fact, is a self-assembly. You see these lines, they are composed of dimers that are facing each other. And if you look at, for example, this molecule, you see that it has 5 neighbors. And therefore, in comparison to the square network that we saw before, you lack this molecule. So you lack this interaction, which is a head-to-tail interaction because the optical dipole is along the n prime axis. And so you expect with the line network to be less redshifted, so a bit blue shifted in comparison to the square network. Experimentally, here you see the solution absorption spectrum of the two molecules, and you see that it's exactly the same. And the self-assembled system, we see something that is consistent with what we predicted, meaning the square network is more redshifted, or the line network is blue shifted in comparison to the square network. And as well, you can see that there is also a redistribution of the oscillator strengths, which is consistent also with this interpretation. Last, here you don't see in this figure, but we also see a 40% decrease of the oscillator strength. And this can be explained with the fact that in this case, your surface density is quite lower than the square network. So this figure shows that intermolecular interactions are present. They can change the absorption spectrum, but they are not dominant since you see these changes are quite small. And to get a bit of insight about what is going on here, and this is, okay, a figure is not going on here. Okay, so just with the number, we implemented a quantum model from Frank Spano and did some modeling of the experiment, and we are able to fit perfectly the experimental data with theoretical data just with these three parameters, which are non-resonant coupling between molecules, resonant coupling, and the surface density of the molecules. And you see that the resonant coupling accounts only for a small part of this intermolecular coupling. And this coupling is what is in our interest, because this coupling produces the oscillator strength increase due to intermolecular interaction. So, in fact, the coupling, the resonant coupling, is even less strong than what we expected before. What about molecule-graphene interactions? So you can have three types of interaction. First, you have a molecule sitting on the graphene surface. So you have electronic interactions that can modify the electronic structure of graphene and the dye. You have a change of molecular conformation, meaning that if you have a polymer, for example, where the cycles are not flat, when it adsorbs on the surface because of the 2D nature of the surface, it can planarize and then change the electronic structure as well of the molecule. And you can have also Coulombic interactions between graphene and the dye, because graphene is highly polarizable. So all this theory is quite complex, and you have to do very complex calculation to predict this. And in our case, we will study experimentally what is going on here. So we found a system where you can have what is called a pedestal molecules that self-assembles on the graphene surface, and a dye that also self-assembles on the surface. And also, you can, by synthesis, put this dye on top of the pedestal and see that it also self-assembles on the surface. So at the end, you are able to have two self-assembled systems on graphene with a dye that is at different distance. Here, so in this case, you break the electronic interactions between the dye and the graphene surface. So here, you will have only the Coulombic interactions between the dye and the graphene. What do we observe for the absorption spectra? So here you see the two molecules spectra in solution. And you see that when the dyes are on top of graphene, there is a pretty big redshift that is reduced by a large amount when the dye is spaced from the graphene surface. And this means that the electronic interactions play a very important role in the absorption spectrum of this system. But you still see some redshift for this system from the solution. So it means that you also have quite big graphene molecule Coulombic interactions. So to summarize what we saw, in this system we have intermolecular Coulombic interactions, which are quite minor. We have interactions Coulombic also with graphene, and the bigger interaction is the electronic one with graphene. And this electronic interaction for us is not good, because it means that a lot of energy will go to the graphene surface. And because we want some fluorescence, we want to avoid this quenching of the fluorescence of the dye. In some cases, you want to have this quenching, for example, to do some Raman experiment. But in our case, because we want to give the energy from the emitter to the plasmon mode, we want to avoid this quenching, which is electronical, Dexter quenching, or a Coulombic, Forster quenching. So what you have to do to observe fluorescence with this system, you really have to space the dye from the graphene surface. So we implemented the same kind of strategy than before, having this dye spaced from the graphene surface with this kind of molecules. And here, the spacer is bigger and more flexible. Therefore, you won't see these regular patterns, but more random patterns due to the flexibility of the chain. And when you look at the fluorescent spectrum, what you observe is a clear signal here in blue of the self-assembled system, which is quite different from the molecule in solution or the molecule just evaporated on a glass substrate. And you see that if you don't use this molecule and just the dye, you won't see any fluorescence at all. And because the fluorescence spectrum is quite different from the two other species, we are confident in saying that it's really a different state of matter. It's really a self-assembled state. But you have some signal, but it's still quite low. And for plasmon amplification, it's not good because your oscillator, your fluorescence cross-section will be too low to obtain some big phenomenons. So still, it was quite an achievement realizing this first fluorescent functionalization of graphene. Because the signal here with this 2D system is too low, you really have to think about using three-dimensional self-assemblies. And three-dimensional self-assemblies require that you have dyes that are fluorescent in their solid state, because you are stacking them, basically, and you really have to have this behavior. So here you see some dye that we used. What are the constraints of plasmon coupling here? So first, you have to find a molecule that you can evaporate on the substrate, and this way you will create this 3D system. Then you want to have this organization constraint because it's what is of our interest, using molecular self-assemblies. You need to have fluorescence in the red region of the spectrum because we are using gold plasmons. And finally, you need to have a quite good fluorescence quantum yield in order to give enough energy from the emitters to the plasmon mode. So the molecule that we used first is this one, is the same aromatic core that we used before, but with the C7 substitution at the extremity. And when you evaporate this system on top of gold, you see here less than 1 nanometer, this atomic force image. You see that it forms islands, and the height of this island corresponds to the length of the molecule. Therefore, we are confident in saying that the molecules stand vertically on the substrate surface. And this organization continues with the layers, as you can see on this image, with islands building on top of other islands, as you can see on this line here. So with this molecule, we validate these two first constraints. What about the photonic properties of this system? So here you see the absorption spectrum of the molecule and the fluorescence spectrum, and you see that it is in the red region of the spectrum, so it validates this constraint. And measuring the quantum yield, we find a quite good quantum yield, which is almost 10%. And what is also interesting for us is this energy difference between the peak of fluorescence and the peak of the absorption. And this is called the Stokes shift. And you really need this Stokes shift if you want to do some stimulated emission, because you need a 4-level system for the dye in order to realize the stimulated emission. So what about the organization? In fact, here we tested another molecule here, this one with a different substitution. And you see that here the organization really plays a role on the photonic properties, because with this system in the absorption spectrum, you are able to completely avoid this transition, which is a transition related to a Frankel excitonic state, which is a delocalized state on several molecules. And this way, we show that here we can really play on the organization to modify the photonic properties. So when you want to do some stimulated emission, you want to have a high population of excited emitters. So you will want to pump a lot your gain medium. And that's what we studied here. And here you see the fluorescent spectra at different pumping powers. And you see that when you pump and pump further, you see a redistribution of the fluorescence spectrum of your system. And if you plot this on a log-log scale, you see that there is clearly a nonlinear dependence of these two peaks here, these two lines representing these two peaks. And this nonlinear dependence, it's really a problem for having some stimulated emission, because here you have less and less fluorescence in comparison to this linear one, this line, which is the slope of 1. And if you have a 10% quantum fluorescence quantum yield at the beginning here you will have a much less, which is you lost one order of magnitude at high pumping power. What about the dynamics of this system? Here as well, when you pump your system, you see that the fluorescence lifetime is decreasing, and this can correlate with the previous measurements, because you can think about exciton recombination, because you have these delocalized states. When you have more and more excited molecules, you can think about two excitons recombining each other non-radiatively. So building a little model for here the dynamics of the fluorescence, we have some linear processes that we can extrapolate from behavior at low pumping power, but we have also these nonlinear processes which are recombination, mainly exciton-exciton recombination at high pumping power. And therefore, we see that in this system, at high pumping power, it's not that efficient than in low pumping power. What about coupling this gain media to plasmonic waveguides? So if we go back to our surface plasmon polariton propagating at the surface of metal, at the interface of a dielectric and a metal, what we usually do for characterizing this system is plotting what is called the dispersion relation, which relates the spatial frequency here of your wave with the temporal frequency of this wave. And this gives this plot, where here you have the spatial frequency in the x direction, and here the frequency in time. And you see that the relationship here, dispersion of the plasmon polariton, is like this. So in reality, to do this, what do? You take your gold layer, and where the surface plasmon propagates here at the interface, you will shine light from the back and vary the incident angle, and we'll see how much light is reflected from this substrate. And what you obtain this kind of figure, where here you have the incident angle and here the energy of your light that you sent. And you see that when the light matches the condition to excite the surface plasmon polariton, you will have a drop in the reflectivity, and all the energy, it means that all the energy goes to, a big part of the energy goes to the surface plasmon polariton, which is absorbed, which has some big losses and absorbed in the gold layer, or which is sent with light, with losses with light in the surrounding. But now what happens if we put this gain media on top of the gold layer? In fact, you will observe this kind of behavior where you see what is called an anti-crossing between the two here lines. And we can wonder why is there, where does it come from, this? So in fact, it's quite simple if you take some assumption, which is a perfect resonator for the die, and some assumption on the dielectric constant on the die. Doing that, analytically, if you take infinite media, you find that the spatial frequency is exactly the spatial frequency for a plasmon propagating at the gold vacuum interface, with this convoluted, in fact, by the refractive index of the die. So if you plot the figure, here you have the refractive index of the die, and here in dash, the dispersion relation for the plasmon at the gold vacuum interface. And you see that the result of this is this kind of behavior, which corresponds to this, because here we had the hypothesis that you don't have any absorption, so you have to add the absorption of the die at the frequency, so you won't see this part of the figure. And what is also interesting is the fact that if you have an emitter, the emitter behaves at the opposite way than the absorber, so you have this behavior for the refractive index, and in this case you don't have any anti-crossing at all, and because emitters emit light only mainly at this frequency, you will have just one point here in your characterization. And that's what we observed, either for both for absorption and emission. And here you can see the experimental data and the theoretical data matching quite well with the 100 milli-electron volt anti-crossing, and the fluorescence experimental data and the theoretical data, which are quite in good agreement. And you see that the gain media is able to send its energy mainly in the SPP mode. And this is very interesting for us because we want to really couple the light of the emitters through to the plasmon mode. So this demonstrates that we are in a strong coupling regime, and show that our 3D self-assembled system are quite good for coupling energy to surface plasmon polaritons. So in summary, with this work, I showed that the 2D die self-assemblies are bringing photonic functions at the nanoscale, absorption, fluorescence, but also vibration that is detailed in the manuscript, but I didn't talk about this in this presentation. And furthermore, you have the possibility to tune these properties. And this is really interesting if you think about the engineering point of view. We also show that 3D self-assemblies are well suited for coupling to plasmonic systems because they send most of their energy, a lot of energy, just in the plasmon mode. But they have some limitation at high pumping power because of these exciton-exciton recombinations that are due to intermolecular interaction. So I want to thank the funding and all the people that worked on these several projects, and I thank you for your attention.